Okay, so let's start. Good afternoon, everyone. Welcome to the afternoon session of the advanced sensing technology. My name is Jinzhe. It's my pleasure to chair this session. In this session, so we have the 4 speakers. The first speaker is from the Deakin University. I would like to invite the James to give the presentation.
Right, thank you, Jinzhe. I'd like to share my screen. And I will present. Right, is that better?
Yes.
Okay, good afternoon, everyone, and good morning to the colleagues, friends in Western Australia. I think there's still a huge time difference between among the states. I'm James Gong from the university, from Deakin University. I'm a lecturer there based at the School of Engineering. Today I'm talking about pipe break early warning through structural health monitoring in Adelaide Smart Water Network. So this is a piece of work I've done with colleagues at the University of Adelaide and also collaborators in SA Water, South Australian Water. So this is the outline of my presentation. So it's 15 minutes, but I'll try to keep it simple and hopefully we have a few minutes at the end for Q&A. So I'll start with some background information about myself. I did my PhD at the University of Adelaide and did my postdocs there as well. Moved to Deakin University last year, June last year, and have been here for just over 1 year. In terms of my background, my PhD was in hydraulics, in particular for pipeline hydraulic simulation and analysis. So that's water infrastructure, so which is slightly different from the bridges and buildings as most colleagues working on. Then I've done pipe condition screening technology during my PhD, and that has been commercialized through a company, Detection Services in Australia. And during my postdoc, I've worked with South Australian Water and also the University of Adelaide, developed a pipe break early warning system, trying to find early cracks on the water pipes so we can do something before they become big enough to burst the pipe and introduce lots of other issues. So today my presentation will focus on this one, this pipe break early warning system. Then before the technical details, just to give you some overview of the smart water network in South Australia. Some people may be aware of this. It started in 2017 officially, and SA Water invested more than $4 million in 2017 to set up the framework, and there have been quite a number of $1 million ongoing investment after that. So this is a smart water network in South Australia today. So we have in the CBD, we have quite heavily placed sensor network, flow meters, water quality meters, acoustic meters, pressure meters, etc. Then across the whole state, we also have some smart meter and some other water quality or other sensors for selected systems for different purposes. Some of them related to structural health monitoring, some of them are more like water quality and some other purposes. So the system I have been worked on is a CBD, the Adelaide CBD water distribution system. And, as said, in this system, we have quite a few different sensing networks for different purposes. And the one I have focused on is this acoustic sensing system. So we have over 300 acoustic sensors installed in the CBD area, which is about 2 by 2.5 kilometers. So the whole area, and in terms of the pipeline, the overall length is about 120 kilometers. Then we have more than 300 acoustic sensors. So they are accelerometer, basically, wireless accelerometers, and they transmit data to the online server every day. Also, just a side view of the other system, which is related to structural health monitoring as well, but this is the transient pressure monitoring system. So that's the high-speed pressure monitoring system. Pressure sensors, basically, we have about 20 pressure sensors installed in this area, and the core purpose there is to detect pipe breaks or pipe bursts once they have occurred. Okay, so why I mention this, because this is something we consider better than doing nothing, but this still too late because it detects bursts as they already happened. Then the acoustic system actually is to serve for the purpose of early warning of pipe breaks and bursts. So we want to find the early cracks, the smaller cracks, before they introduce pipe bursts. So this is more advanced. So we consider this is a truly preventative, or at least more preventative measure than the pipe burst detection, which is better than the past practice, but still quite reactive because it's already occurred. We just know it, probably as quickly as we can. Then we do something. But here, what we're trying to do here is really capture those newly developed small cracks so we can prevent the burst events. So this is a photo of the sensors we used in the field. So this is just a typical manhole on the straight, and most of the pipes are buried underground. We can only access the system through the manholes and other existing openings. So here we have a manhole, and underneath here we have a fire hydrant. Okay, this is a fire hydrant in South Australia, and also it serves as air valve as well. So we attach the accelerometer on the fittings. We find a flat surface and magnetically attach that to the fitting. Then the accelerometer is connected to a logger, data logger, battery powered, and then this is a antenna. Then we transmit data through the 3G network, and now they have developed the 4G version of the sensor. So here is a screenshot of the dashboard that the operators would say. Here we have this dashboard with a map of the CBD, and you can see all the locations of the sensors, not just that acoustic system, but also other systems incorporated in this dashboard as well. And also within the system, it can generate some alerts or some alarms. What we found was the simple alarms, generated by this product as off the shelf from a company. They are not not accurate enough, so you end up with hundreds of false alarms every day. So nobody can really cope with that. So then we as researchers, we get involved to develop the data analytics to really generate meaningful alarms for the operators to understand the system and to respond to the real cracks on pipes. Then at the bottom, we see a screenshot of the so-called acoustic noise level. So this is a dimensionless number, although on the y-axis it says dB. Actually, it's not dB, but that dashboard, they just put on the dB as a unit. But the sensors are from another company, and they don't really release detailed information in terms of how they convert the raw data into this single value, the noise level. They only call this as a noise level, without giving much information about how this is derived. But anyway, that's a single value, and we were told this is related to the energy level of the noise as measured by the sensors. Then we can see the so-called noise level can be measured every, say, half an hour in this case, and we can configure this to like every 10 minutes. Then during the so-called quiet night time between 2 a.m. and 4 a.m., we typically have a higher resolution, temporal resolution, so 5-minute logging intervals for the so-called noise level. And also at about 2 a.m. in the morning, we have 10 seconds of wave fire, which is the raw data. So the wave fire as captured by the accelerometers with a sampling rate around 4,800 Hertz, but only 10 seconds per day. So these are the data we are dealing with. Then here we show you an example of the success detection of a pipe crack. So at the background, that's a map which shows the location. So if anyone is familiar with Adelaide, so this is Henley Strait in the CBD, which is probably the very busy area in Adelaide City. And here we have a logger POS 14, which is the acoustic accelerometer. Then on the 22nd of July, we consider this as a normal condition, as a background condition. Then on the 23rd, we see an increase in the frequency range. So when we do the frequency analysis of the Wi-Fi, we see an increase in the higher frequency components, and this continued to the 24th of July. Then back to the dashboard, we have the so-called noise level as provided by the sensors. We say that up to 22nd, the noise level was relatively low. On the 23rd, the noise level suddenly jumped up, and on the 24th, the noise level increased again. Okay, so this just shows the principles behind, which is quite straightforward. So we're looking for change, comparing with historical data, and we are looking for change from both the noise level perspective and also the wave fire, from the frequency domain perspective and the time domain perspective as well. Then what we did was, once we found something on the 23rd, we thought this is quite suspicious, so we sent field crew to the site and did some visual inspection, and also we have some other correlator-based leak detection tools, acoustic correlators, listening sticks. So they have been trained, the field crew have been trained to do on-site leak detection. So we sent them there and they did some investigation, and they found it's most likely there is crack, through-wall crack, which also can consider as a leakage underneath. So what they did was block this area, put all the signs, reduce the pressure for that particular water main, and put notice. And all of this has been done without any notice of the water customers. So this is the so-called preventative or proactive asset management as we trying to achieve. Because in the past, what the most times it's the customers, the water customers who are affected by the bursts or the leakage, or who walking on the street and saw the water flooding on the street. Then they notice the water utility, say, hey, something going on. So you got a bursting pipe, you got leakage, you're wasting water. Then they tell the water utility. Then the water utility have to react. At that point, and which makes them really looking very bad, publicly from the PR perspective. So we're trying to change the situation. We're trying to say, look, we want to find the problem before the customers, before this affect the water customers. So that's on the 23rd. Then on the 24th, we saw, oh, this continued, and definitely there's something happening. So, and also the field investigation confirmed that there definitely is a leak in that area. So they dug it up, and here, this is a photo of the pipe as we just, dug the whole pipe out of, not the whole pipe, but that area out of the ground, we see that this is already under reduced pressure condition. So the pressure was 55 meters, on normal conditions. Here, not sure about the pressure, but it's already reduced from the standard. We can see the water just gushing out of the leak. It is a circumferential crack, basically a circumferential crack on a DN100 cast iron main. And after cutting off this section and replace a new section, we also had a look of the pipe. Basically, only like 1 to 2 inch pipe wall still connected. The rest they have just cracked. So if we haven't done anything, so this will become a burst in no time. So this is a summary of the performance. So we've done the R&D for about 2 years, and we, as researchers and R&D engineers, we closely monitor the system and develop an algorithm for them. And here we see we have prevented 45% uncontrolled pipe breaks within this 2-year period. And after June 2019, this system has been handed over to the operational team in IC Water. So it's out of the hands of the researchers. It's truly transferred to the operators in the OCC. They call the Operation Control Center. And they only look at the meaningful alarms. So there will be only maybe 1 or 2 per day, not hundreds. And most of them are true alarms. So it's really practical now. And we lost the track of the the success rate, this and that, but we probably can get the information at some stage. The key challenge I didn't talk too much. Differentiating the real signals from cracks, from the leaks, from other types of signals, especially in cities. In busy cities, you got all sorts of noise. If you put a accelerometer in a city, you just listen, you will find all sorts of funny things. People talking, singing, traffic, ambulance, you name it. So the challenge here is really tell which is a real, pipe crack or pipe leakage. So we generate meaningful alarms, to reduce the number of false alarms. So make this system practical. So this is a key challenge. For technical details, please refer to the 3 papers already published. We are publishing, more papers, especially on machine learning-based techniques to, further enhance the performance of the signal analysis. The last bit is a partnership. So that just to briefly touch this as time's up. So this is a large project I'm presenting here today, but this is a group effort, lots of people involved, $1 million investment. So not something a single researcher can do. So that's all for my presentation, and any questions are welcome.
Thanks, James, for your interesting presentation. So, any questions or comments for James from the audience?
Hello, is that clear?
Yeah.
Yeah, it's right. Anthony Schofield here from Arup. I think that presentation just shows the importance of having the baseline data, so you can compare that when something goes wrong with the baseline data, where if you were trying to calculate a defect from analytical approach, it's going to be very, very difficult. I think for infrastructure providers, because I work with bridges and highway structures, it's about how do you go about persuading the client that you will get, that they need to get the background data to be able to understand when something isn't correct, and that's the, because they're going to make a multi million investment with no clear expectation of when they might get a return from that, although the return would probably be quite substantial, but that's very difficult in economic terms to make it stack up. Don't know if anybody else has anything to add on that sort of observation rather than question.
Yes, that's absolutely right. The permanent monitoring or the digital twins or the smart systems, whatever you want to call them, provides the ability to have historical data to compare with, so which is very powerful. But again, as I asked a question earlier today, that this whole system is so costly, and the asset owners or the operators, it's difficult for them to put up their business case to justify such an investment. So this is in the CBD, which is a very important area, and it bursts, not just to lose water and cost them money to fix a pipe, but also damage properties and public damage their publicity. So that's why it's easier to justify to spend $1 million to do this. But in other suburbs, for example, they're not thinking expand this to the whole state because it's too costly. You can't justify that in suburbs. In suburbs, it's probably still more reactive based asset management. I guess that's a big issue, across the infrastructure sector. How do you justify your investment? Yes, these new technologies, structured health monitoring, they are very useful, very helpful, but very costly. How do you justify that?
All I can say is hang on for my talk, guys. Because hopefully I'll be able to answer that question, James. Thanks for the good presentation.
Right.
Okay, concerning time, maybe move on. Thanks, James, for your great presentation.